Hey everyone, and welcome. Today, we're diving into some truly mind-blowing technology, catheter-based medical devices. This is the world of surgery without a scalpel, where doctors can travel deep inside our bodies to fix things that used to require massive, open operations. It's pretty incredible stuff, so let's get right into it. So, here's our game plan. We'll start with a big idea, this whole minimally invasive revolution. Then we'll actually break down the toolkit piece by piece. We're going to look at the tiny tools doing all the work, the wild materials that make them possible, the insane engineering challenges, and finally, why with these devices, failure just isn't an option. All right, first up, this idea of a minimally invasive revolution. We're talking about doing unbelievably complex procedures, like fixing a blocked artery in your heart or stopping bleeding in your stomach, all through an opening so small you could cover it with a Band-Aid. It's a total game changer.
And that really begs the question, right? How on earth do you repair a delicate blood vessel deep inside a beating heart? Or deal with an issue in your GI tract without, cutting a person wide open? Well, the answer is in a system that is just unbelievably sophisticated and elegant.
Okay, so how does it all work? Let's break down this high-tech toolkit. From the outside, it might not look like much, but it is an absolute marvel of engineering. You've got several critical parts that all have to work together in perfect harmony. Everything, and I mean everything, starts with the guidewire. You can think of it like the advanced scout, but the railroad track analogy is perfect. It's this super thin, super flexible, but also steerable wire that the doctor carefully threads through the body's winding highways of arteries to lay down a path right to the problem spot. And once that track is laid down, well, the train can finally leave the station, and that train is the catheter or the sheath. It's basically a hollow tube that just slides right over that guide wire, acting as the perfect delivery tunnel. This is the vehicle that carries all the important cargo, the tools and therapies, exactly where they need to be.
So who's driving this train? The doctor is, and they're using the handle. This is the control center, the part that stays outside the body. It's painstakingly designed to be like an extension of the surgeon's own hands, giving them this incredibly precise control to steer, to rotate, and to deploy whatever tool is at the very tip. It's all about fine-tuned, intuitive control.
And this brings us to what I think is the coolest part, the business end of the device. You would not believe the variety of microscopic tools that can be attached to the tip of a catheter. Each one is a tiny marvel, built to do a very specific job deep inside the human body. You know, the first real revolution in this space was balloon angioplasty, way back in the 70s. And the concept was just brilliant. You guide a tiny balloon to a blockage in an artery, inflate it to basically squash the plaque flat against the artery walls, and then you deflate it and pull it out. Blood flow restored. It completely changed medicine, but it wasn't perfect. Sometimes the vessel would just collapse again. So the answer to that problem was the stent. This is a tiny little mesh tube that's fitted over the balloon. When the balloon inflates, it expands the stent and presses it against the artery wall. The stent then locks in place, and it stays there permanently, acting like a scaffold to prop the artery open. This was a massive leap forward. And this toolkit goes way beyond the heart. In the gastrointestinal tract, for example, doctors can deploy these tiny little endoscopic clips. They can use them to literally clip a bleeding vessel shut, or to mark a spot for surgery later, or even to close up a small tear, all without a single stitch. Or check this out, another really simple but genius tool, ligation bands. These are basically tiny little rubber bands that are delivered through an endoscope. Doctors use them to tie off swollen veins in the esophagus or to treat hemorrhoids. It just cuts off the blood supply and the problem goes away. So simple, so effective. So you have to be asking yourself, how is any of this even possible? I mean, how do you build something that's strong enough to prop open an artery, but flexible enough to snake its way through the entire body to get there? Well, it all comes down to the incredible science of advanced materials. Let's just take stents, for example. The metal you choose is absolutely critical. The first ones, they were made of 316L stainless steel, a good, reliable workhorse. But then came cobalt chromium alloys. These have a much higher radial strength, which means you can make the walls of the stent way thinner, making it more flexible. And then you have the true game changer, nitinol. It's a nickel titanium alloy with shape memory. This is wild. It means you can scrunch it down when it's cool, deliver it, and then as it warms up to body temperature, it automatically springs back to its original expanded shape. Perfect for self-expanding stents. Really, it's all about this amazing partnership between materials. On one hand, you've got the metals, stainless steel, nitinol. They provide the raw strength, the scaffolding. But on the other hand, you have the polymers.
things like nylon and paybacks. They're the ones that give the catheter shafts its incredible flexibility and allow the balloons to inflate and deflate in a perfectly controlled, predictable way. Look, building these devices is not for the faint of heart. It is a true engineering gauntlet. It's just one incredibly tough challenge after another that has to be solved to make a device that doesn't just work, but is fundamentally safe for a human being. Engineers are in this constant balancing act. A device has to be flexible enough to navigate the winding roads of our arteries without kinking, but also pushable enough so the doctor can actually get it there. When the doctor twists the handle, that rotation has to transfer perfectly to the tip, maybe meters away. And if you put a stent in a heart, it has to be able to withstand millions of heartbeats every year without breaking. And of course, deployment has to work perfectly, 100% of the time. This quote here just says it all. It says that forming the balloon is both an art and a science. Think about that. You're transforming a simple polymer tube into this incredibly precise, thin-walled balloon. The heat, the pressure, the timing, if the wall thickness is off by just a few microns, that's smaller than a human hair, it could completely change how the device performs inside a patient. And that leads us to maybe the most critical point of all. When you're engineering something that's going to be placed inside a person's heart or their brain or one of their major arteries, there is just zero room for error. Failure is, quite literally, not an option. And these aren't just theoretical risks. This is real. These are examples from actual FDA recalls. A catheter tip can break off and cause a stroke. A balloon can get stuck inflated, blocking off a critical blood vessel. These failures can have absolutely devastating consequences for a patient, and that's exactly why the engineering and the testing are so unbelievably rigorous. So the direct response to those horrible risks is this: a massive battery of tests. Every single one of those engineering challenges we just talked about, it gets tested relentlessly. They test the balloon's burst pressure. They test the strength of the tip attachment. They put it on a machine to simulate millions of heartbeats. Every single aspect is measured, quantified, and validated to make absolutely sure it's safe before it ever goes near a patient. And that kind of leaves us with one final thought to chew on. We've gone from a pretty simple balloon on a wire to these incredibly complex systems that involve software and smart materials. As these life-saving machines get even smarter and more powerful, the challenge of making sure they are 100% safe only gets bigger. And that's the central question that engineers, doctors, and regulators are going to be tackling for a long, long time.